I'm Corentin. I work on research at Radium, so it's a medical company. I'll talk a little bit about it. And here I'm going to do a very research-focused talk. So this is about a research paper that we submitted to NeurIP. So we're just working on the rebuttal now. Maybe some other people are also doing this right now. So yeah, let's get started. So yeah, a little bit an intro about AI and radiology. So yeah, radiology, it's a very huge medical field. It's growing a lot. It's like the main way to diagnose a lot of diseases, and it's growing every year in like quantity and in complexity. But we don't train a lot more radiologists now that we used to, and so it's there is a shortage. It's a field that has a lot of tension, and so AI has some promises here to help radiologists to be much faster and be more efficient, but there is still very little adoption of AI. Around 30% of radiologists use AI like frequently, and there are a lot of devices, like FDA-cleared devices that are using AI, but they all focus on very niche, specific tasks, and so it's kind of painful to use the tools. You have to switch from one tool to another. They don't communicate well. And so yeah, it's quite hard to use. And so yeah, the limitations that the current AI models have, so there is not really an AI native integrated software to use the tools. Most radiologists, they use like very old tools from the 90s or the 2000s that weren't designed for AI. And also the models are very fragmented. As I said, you don't have a model that can do everything. And so this is what the startup Radium is working on, to build a universal AI for radiology. So yeah, we are trying to train foundation models that can span all the modalities, all the body parts, all the diseases, and that are state-of-the-art for all the medical tasks. That are also promptable, so you can like maybe write some prompts to the model to steer their behavior. You can correct when there is a mistake, so you don't just get a basic answer which is not modifiable very easily, like segmentation, which could be wrong. So yeah, we work a lot with a human in the loop to correct and refine the annotations. And so yeah, we build a product for doctors, and it also enables us at the research team to test our models with doctors and iterate on it very efficiently. And so yeah, I'm going to present our latest work, Jolia. So it's a foundation model for 3D CT. So I explain in a bit what CT is. And here the particularity is that we train the model using radiology reports along with medical images. So it's a follow-up on one of our previous work, which was called Curia, which was self-supervised learning on CT and MRI images. So it was using only images, and it works pretty well, but it's a bit limited because you are missing a lot of information that is contained in the reports. The report can guide the vision model to learn to extract all the abnormalities, all the disease, and so yeah, it gives a much better model. But it's quite hard to train because the image is huge, the reports are quite long, so I'll get into more details. And so yeah, a little bit of intro about computed tomography, so CT, or scanner in French. So it's basically a 3D radiography or X-ray, and it gives you a lot of slices to look inside the human body. So here this is a brain. You can see all the slices from the top of the head to the bottom. You can also view in multiple axes. So here it's like from top to bottom, left to right, left to right, and so yeah, you can slice and view in different ways. Even slice not in orthogonal axes if you want. And it can be used to detect most abnormalities in the body. Some things cannot be seen with CT. You have to use MRI, but it's a very broad tool. And so our goal is to train an AI model to predict abnormalities from the image, and also to maybe write the radiology report. If it can detect all the abnormalities, then it might as well write the report. And so we want to train a very general model, not just focused on one specific disease, but a model that can predict everything. And so one way to pre-train models like this is to use image-text alignment, so CLIP. It's a very common algorithm to train deep learning models when you have an image and a text. You just use a vision model that gives you an embedding of your image, use a LLM, a text model that gives you a text embedding, and then you align the two vectors with contrastive learning. And so this works quite well, and it's used also in medical imaging. But one issue we have in radiology is that it compresses a lot the information. And here we have radiology reports which are very long. They can contain 200 to 400 or plus words. So sometimes it's like one page of detailed notes describing every organ in the image. And similarly, the image contains a lot of detail. You can see every organ, dozens of organs, and so by compressing everything to a single vector, you lose a lot of information that maybe could be better leveraged. And some methods use like segmentation masks. They like segment every organ, and then maybe they do cropping around each organ and try to align one organ with the description of this organ. So this works quite well. It works better than CLIP, but it has some drawbacks. It's limited to the regions that are supported by the segmentation model, obviously, and it's very dependent on the accuracy of the segmentation model. Some organs are very hard to segment because they are quite blurry, and so it has some limitations which we try to address here. And so the main goal of this paper is to learn a fine-grained alignment between local parts of the image and some text subsections without using any mask, only with learning where to look on the image to align to a specific region. And so I'll get now into details of the method. So it's a complex image, but I'll get into details of each part. And so first we have the standard CLIP loss. So as I said previously, we have the vision encoder, which will project all the image into some embeddings. So here it's a 3D volume, so we have some 3D tokens. Like the image is decomposed into patches because we use transformer-like architectures. And then we have some pooling function, which gives us one single embedding. And we can do the same thing for the text. We just pull it with the text encoder into a single embedding, and we do some global alignment. But then we want to do some local alignment as well. So first, for the text, it's quite easy now with like LLM pipelines. What we do is some preprocessing to just split the report into some organ related sections. And it's quite easy also because usually radiology reports, they are already very structured. Radiologists describe first the liver, then the lung, etc. So here we can see concept 1 liver, the hepatic and portal veins are patent. Lungs, small bilateral pleural effusions, etc. So we just decompose into sections something that is already quite well structured. And then we embed all the sections into their own embedding. And so we can see here a full example of a report with the thyroid, trachea, lungs, heart, aorta, mediastinum, and upper abdomen. And so we want to do similar things for the image so that we can align the local regions with their text representations, such that the model can learn some better and fine-grained alignment. And so it's hard because we don't want to use segmentation masks. So how we do it here, we use some queries with a cross-attention layer. So at initialization, we create k random learnable queries, one for each organ. So we have actually a list of organs. It's a predefined list. We have like 100 organs in the taxonomy. And so we initialize one random vector for each organ, and this random vector will be used as a query for a cross-attention layer, which is also learned during the training with the vision encoder. And so this will pull the full embeddings of the 3D volume into specific concept representations. So I will have one vector that represents the liver, one vector that represents the lung, one that represents the brain, etc. And so it's at the beginning it will be completely random because there is no supervision on how the model is supposed to pull the concepts. But the hope is that because those queries, those vectors will be aligned with the text representations, the model will learn to pull the correct region. And so yeah, this is the pair concept alignment. So we have k image vectors, k text vectors, and we have k similarity matrices that are trained in a similar way to the global alignment. It's standard clip training. So we enforce that the text vector for the liver is similar to the image vector to the liver, and is dissimilar, I mean, for the same image and text that are already a pair in the dataset. But for one image and a different report that describes another image, then we push apart this liver image representation with the text of another liver from the dataset. So yeah, this then forces the alignment, the local alignments. And so yeah, and for the training, so it's trained on 67,000 CT. So for this paper, we used only public exam and report pairs. So it's better, so it's easier to reproduce. So it has chest CT and abdominal CT. And yeah, as I said, the architecture, it's an Atlas 3D transformer. So it's kind of like a vision transformer, but it has multiple scales. So we do some patches at resolution 16 by 16, 8 by 8, 32 by 32. So the model can look at finer grain details and also some more global vectors. But we also tried with ResNet and other architectures, and it works also well in practice. And it's trained on the H100 for around 2 days on Janzé. So we used a public HPC cloud for this project. And so the first thing I want to highlight is not some numerical results, it's the visualization of the attention maps. So as I said, there is no supervision. So here we look at each query. So for example, the liver query that is supposed to learn to attend the liver. And we look at where the model is focusing on the whole CT. And so I think most of you will have to trust me because you might not know where the liver is, but yeah, this is the liver here. And so the model learns to attend to a specific subpart of the liver, but if we look into the other axis, it's focusing on the liver, which is here. The lungs, we have two lungs, one here and one here, so it's a bit biased toward one of the two lungs here, but yeah, it's actually looking at both. The kidneys, so we have two kidneys, left and right, and it learned to similarly look at the kidneys, similarly for the colon and the hips. And so yeah, this was quite surprising for us that it learns to attend the correct region. So those are the most common organs that are described in the reports. For some that are not very often described, it doesn't work as well, obviously. The model might learn more data to look at them. But for those organs, it works quite reliably. Those are not like cherry-picked images. The organs are cherry-picked because those ones work well, but yeah, the images are very, I mean, it's quite reliable. So yeah, then we can get a bit into the main results. So the task that is the most interesting to us, it's finding classification. So this means classifying all the abnormalities that we can see in a CT, in a 3D image. And so to construct this task, we use again an LLM pipeline because we don't have very large annotated data sets that give us all the abnormalities, all the classes that we have in one image, but we have the radiology report. And so we can just ask the LLM to extract some classification tags from the report. So we defined a list, a taxonomy of findings. We have around 300 classes for abdominal and for chest CT. And so, yeah, for example, here the report might say large left pleural effusion with atelectasis progressed from prior exam. And so the two classes extracted from this are pleural effusion and atelectasis. So it's a task that seems quite easy, but sometimes there are a lot of synonyms of medical terms that have some different meaning depending on the context. So it's not a perfect pipeline, but the LLMs, like commercial LLMs, are starting to be quite good at medical understanding. So it's we checked with the radiologists and it's quite reliable. And so and then the objective is quite simple. It's just to predict all those classes from the 3D volume. And we do some linear probing evaluation. So this means we completely freeze the text encoder, which is first pre-trained with the alignment loss. And we train a linear layer on top of the features to predict all the findings at once, so the 300 findings. And one different here compared to regular linear probing is, since we have all those queries which gives us representations of one specific organ, we can leverage them here. And so instead of using just the class token like we would normally do in linear probing, which describe the full image, we concatenate this global token with the organ that is associated with this finding, because every finding is associated with only one organ. And so then a big table of results, but basically it works quite well. So here we see the clip baseline is this line here. So this is AUC metric, so it has 82 AUC, 82.4 AUC on average. And with this method, we get 84, so an improvement of 2 points over the baseline. And it's so state of the art compared to other open source models. And we also try to do linear probing only on the class token to see do we also improve this representation. And we do, like we go from 82.4 to 83.1. So it's halfway towards the best score. So with this method, we also improve global representations as well as the local ones. So this is the main results of the paper. We also look at zero shot, because clip pipelines are often evaluated in zero shot. It's very practical because you don't need to do any fine tuning. You just prompt the model with, for example, a photo of it's quite small here, but a photo of a cat. And then you encode this text with the text encoder, and if you have 3 labels, then you take the one which has the highest similarity between your image and one of the 3 texts. So we could try to use zero shot as well to classify medical findings. But one issue with this is that the model are trained to align full reports, not just one sentence, which is the presence of pneumonia or absence of pneumonia. And so short sentences are a bit out of distribution and it doesn't work so well. We tried with a lot of different prompts, finding or no finding, there is evidence of or there is no evidence of. So these are sentences that appear a lot in medical reports. And it works fairly well. We get 74 AUC, but it's much lower than the linear probing results, which was I think 80. This is CT rate, so 86, and 84 for the baseline, 85. So it doesn't work as well. And so we use another method here that works much better, and we use full reports as prompts. And so we for a given abnormality, we sample 50 reports that contain this abnormality and 50 that doesn't contain this abnormality. And we embed the two reports with the text encoder, and then we do the average of those embeddings, the 50 positive and the 50 negative, and we use those embeddings as prototypes to find the best, to find the correct answer. And yeah, so here is the number of reports that are used to build the prototypes, and we see that it increases a lot the results, and we reach around 80% AUC, so much better than this 74 here. And it improves for all models similarly, so it's a much better method for medical imaging. And the final task that we evaluate in the paper is report generation, because that's kind of the end goal for an AI model for radiology. If we could just go from the image to the report, the task is solved, then the radiologist can just quit and go to the beach. But yeah, here we have the ground truth report, so we see it's very long, it contains a lot of details. And what we do is we fine-tune a Qwen 3.5 decoder to generate the report from the features. So we give we add the features as input to the decoder, and we do some two-stage training. So two-stage training. So we follow Lava, similar pipelines than Lava for those who know. So we first train only a projection layer, and then we fine-tune the text decoder with LoRa. And we keep the vision encoder frozen here, but this could be future work to defreeze it to improve the results again. And we evaluate it with NLP metrics and clinical metrics. So here, NLP metrics are quite bad. You see the text is very long. It contains a lot of scientific terms which have a lot of synonyms. So metrics like bleu or rouge will not be very accurate here. So yeah, people have developed other metrics like rad, graph, green, and crimson, which basically usually convert the report into a graph with, again, a taxonomy of medical terms, and then compare the two graphs to check if it contains the right information. And so, yeah, the results with Jolia seem much better than previous models that were open sourced. But if we look at the results in practice, it's still very far from a good report. Usually the model kind of collapses to some templates that are often present in radiology reports. And so it's still very far to be usable in practice. The finding classification is pretty reliable, but this part still has a long way to go to be useful for medical practice. And so the model is actually deployed in our viewer. So we can ask what finding do you see, and then there is an orchestrator here which will call the right model and detect it. So here it says kidney simple cyst, and so this is a kidney cyst that you see. It's a big mass in the kidney. And so having this model here allows us to test and iterate very fast with the radiologist. So we have radiologists in the team that work with us to understand, annotate the image, and understand the problem, because usually we can't read the image as machine learning researchers. It's quite hard for us to understand what the model is predicting usually. So the future works. Something we are doing now is scaling with internal data, so 300 and more pairs of CT and MRI with text reports. So this might seem not so big compared to like natural images or clip data set with clip. But you have to remember that it's a very long report. So if we structure it into multiple subparts, sometimes it gives us like 10 times many pairs, or 20 or 50 times many pairs. So it's starting to be a pretty large-scale data set. And also, CT and MRI are very big in shape, and so it's a lot of engineering efforts to pre-process the data. We have hundreds of terabytes of radiology images which are used to train this model. And yeah, then some research directions we are investigating, fine-tuning the text encoder for better zero-shot performances, because for now it was frozen. Some organs which are very rarely described don't get a lot of signal during training. And then some new tasks that we are looking at right now to localize the findings, because radiologists, when they see that the model detected something, they want to be able to go very quickly to where the model saw the finding. And for now, with the attention map, we can bring the radiologist to the organ, but not to the specific zone of the finding. And some organs are very big, like the lungs. It's a large part of the body, so it's still some work for the radiologist to find the finding. And so yeah, we are working on also text generation, so how we can improve the report generation, or maybe just description of individual findings, which might be easier than trying to generate the full report at once, which can contain a lot of hallucination. And so yeah, we're trying to improve representations for those two tasks, localization and text generation, maybe with multiple losses, so adding SSL, which might improve dense tasks like localization, also classification loss. So yeah, thanks a lot. The model is open source and the paper is on archive, you can check it. So yeah, thank you.